Hi there, welcome to my channel. My name is Prabjot Kaur. In today's video, we're going to review another remarkable paper in the field of speech processing. This is a paper that was presented by Facebook in 2021. So it's a relatively old paper considering the pace at which AI is currently moving. However, for some of you who have been following the recent content on my channel, you probably know that we have been reviewing and reading the papers in the domain of direct speech-to-speech translation. So as I was reading more and more papers for direct speech-to-speech translation, I found out that some of the recent papers were using HuBERT. So that's what motivated me to learn more about what HuBERT is, and that's what I'm gonna share with you in the video today. So without further ado, let's get into the details. First of all, I must say that I really like the title of this paper because everything that's presented in this paper, the crux of that is in the title itself. So we'll break down the title first and then we will go into the details. Okay, so let's start with HuBERT. Now, if you are in the field of NLP, you may have already read a paper, a phenomenal paper called BERT. If you haven't read that, I highly encourage you to read this paper because this is one of the phenomenal paper in the NLP for processing text. In this paper, the authors present a technique called masked language modeling for training a model. And this same technique is used by HuBERT, but the difference is that here they're applying BERT for speech. And this whole paper is about how do we apply BERT to speech, which is a little bit challenging because speech is a continuous input, whereas text is not continuous input. So this is the method of how we apply BERT to speech. And that's where this other part of the term comes into play. HU is called hidden unit. I will understand what that is in a little bit. Okay, so next part of the title says self-supervised. So they are using a method for training a model, and the method that they're using for training a model is called self-supervised. And this method is used for what purposes? So using self-supervised method of training for speech representation learning means how we can represent speech. So we want to learn that. And how are we doing that? We are doing that by masked prediction of hidden units. Now, this may not be making sense to you because it's a little bit complicated. I totally agree with you. I actually read the paper a few times and now I can understand the paper by the title. So I want you to also, or at least I wish that after we go through this video and you read the paper a few times, you come to the same understanding that this title is really what the paper is all about. Now, what is self-supervised? Self-supervised, the formal definition is it's a machine learning process where the model trains itself to learn one part of the input from another part of the input. So the labels are auto-generated. Now, if you are familiar with deep learning, you probably know that when we train a model, there are different ways we can train a model. We have unsupervised, we have a supervised method. For unsupervised, we do not need any labels to train a model. However, for supervised, we do need the labels for training the model. Now, when it comes to supervised, we can have fully supervised, we can have self-supervised, we can have semi-supervised. So the method that is used here is called self-supervised. Yeah, so let's take an example and understand how we apply self-supervision in the context of masked language modeling. So I'll start with a text input because it's easier to understand. Let's say we have an input. It's a sentence, and the sentence is, I love my dog. The goal here is we want to train a model, and that model can be a transformer model, for an example. And the way we do the training is, first we break the input into discrete units. In this case, it's easy because we already have the sentence broken down into words, and we can consider each of this word as a discrete unit of the input. So what we do is, rather than giving the entire input, in other words, rather than giving all the units of the input to the model, what we do is we mask or hide some of the input units from the model. So let's say I mask this input, or I hide this input from the model, and I feed the model this, 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 and this is masked. So the goal here is we want to train our model to be able to predict this masked input from the other parts of the input. So that's why this is called self-supervision, because here we are generating the targets. So target is nothing but this missing word, and we're generating the targets from the input itself. So it's self-supervision. So that's what self-supervision is in the context of, or how it's used for masked language modeling. I hope this makes sense, because we will be understanding or applying this in the rest of the paper. All right, so now we understand what is self-supervision. The next part of the paper says speech representation learning. So it's just saying that because speech is a continuous input as opposed to text, so we want to be able to represent speech in discrete units. Just like we have text, in the text we have sentences, and we can easily break down these sentences into words, and each word is a discrete unit. But in the case of speech, it's not that simple. Speech is a continuous input. So here we want to be able to represent continuous speech by discrete units. And those discrete units are called hidden units in this paper. So that's what we want to learn. And then how we are learning that is by masked prediction of hidden units. So there's a lot of details here, and let's go get into the paper, and I'm sure you will understand it as we dive into the details. Once again, the authors propose the hidden unit BERT approach for self-supervised speech representation learning, and they show that this method either outperforms or matches the performance of other state-of-the-art models such as Wave2Vec 2.0. So let's dive into the model directly, and then maybe we'll come back and review some of the points that I've highlighted here. Okay, so this is the model. So this entire framework is actually composed of two steps. The first step is to create targets, and then the second step is for the model to predict the targets for the masked input. Now, why this is important? Why do we need these two steps? For that, let's go back into the HuBERT model again. Okay, so for the HuBERT model, we have a method called masked language modeling that was proposed. So here the input was a sentence, a text input. So here the text input, we can easily break it down into words, and those words are discrete units. So when we feed that sentence into the HuBERT model, we can easily mask or hide some of the words because the sentence is already broken down into words. And then what the model does is model learns during the training process, model learns and it tries to predict what that masked or the hidden word is when it's given rest of the part of the input. Now, in case of speech, we have a little bit of a complication, right? Because speech is a continuous input. So we do not have these discrete inputs that are going into the model, right? So we have a continuous speech. So that's why we need two steps for processing speech the same way we process text in BERT. So that's why the first step here is to create those targets, and that is done by a method called k-means clustering. We'll go into the details, but here just understand that this whole training process actually has two steps in it. One, we first create the targets, and then in the second step, we train the model to predict the targets for the masked positions of the input. Now, I must say that this original diagram in the paper is not very explicit. At least to me, it wasn't explicit the first time I read it. So I actually went online, tried to search for other resources that explained it in a little bit more detail, and I found this excellent resource. It's a blog written by Jonathan that breaks down the original diagram in the original paper into more details. So we'll go into this blog and the diagrams in this blog, and then maybe we go back to the paper and try to compare, and we understand that better. Okay, so as was mentioned before, there are two steps in the training process that alternate between each other. The first step is to generate these targets, which the paper also called hidden units. And then the second step is the model tries to predict the hidden units or the targets for the masked portion of the input. So let's go into the details. For the first step, which is to discover or create these hidden units or the targets, the method that the authors use is simply k-means clustering. So let's start with the initial input. So initially we have this raw waveform, which is a continuous input. So for the first iteration, again, this is the exception for the first iteration, the continuous input raw waveform is first converted to a discrete input. So for the first iteration, the authors specifically extract MFCC features. So this x0, x1 for the first iteration are just MFCC features. So you can see that these are discrete, right? So we converted the continuous input to a discrete input. Then we apply the clustering, k-means clustering. The k-means clustering simply clusters the similar parts of the inputs into clusters. So here in this example, we have 3 clusters. So all the parts of the input, they will belong to one of these 3 clusters. And then the cluster, each cluster is represented by a unique embedding. So for example, anything that belongs to this green cluster is represented by embedding E2, E2, E2. Anything that belongs to this orange cluster is represented by embedding E1, 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 and anything that belongs to cluster yellow cluster is represented by E3, 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 E3. So these are our hidden units. So this we call this discovering the hidden units or the targets. And then in the next step, we want to predict these hidden units for the part of the input that is masked. Okay, so now we understand this first step. Let's move on to the prediction step. In the prediction step, again, we start with the raw waveform. So this is a raw continuous input. The first thing we have to do is we need to convert this continuous input into a discrete representation, and that is done by a CNN encoder. So the CNN encoder converts this continuous input into latent features. So these are nothing but the discrete embeddings for the raw continuous input. So once we have these latent features, after we have passed this continuous waveform into the CNN encoder, what we get is this. Here it's called Z. Then we want to pass this input into a BERT encoder. Now we apply what was presented in the HuBERT model, which was called masked language modeling. So what we do is this input that goes into the BERT encoder, we mask some of these inputs, and the goal is that the model, we want to train the model so that it's able to predict what was there, what was the input that was masked. Okay, so again, why do we need to do these two things? So first, CNN encoder basically encodes the continuous input into discrete units, and then we mask some of these input, and we want the models to be able to predict those. Why we use BERT encoder or context network is because this is a continuous input. It's a long input. This BERT encoder or transformer encoder, it helps us learn the relationship between all parts of the input. So that's why we're using this context network. So then this context network, during the training process, it learns to predict the output. Specifically, we are interested in learning this. Specifically, we're interested in knowing what the model predicts for the units that were masked. So here we get some output from the context network, and then we compare whatever the model outputs here with the actual targets or discrete unit that were created in the first part of the process. So we compare each of these vectors to these embeddings by cosine similarity, and then we essentially apply cross entropy loss to understand how far the prediction is from the actual targets, and then the training process repeats. So one important thing here to consider is that when the authors apply cross entropy loss, they only apply this to the masked input. So what we mean by that is, let's go back to the paper. Actually, let's go back to the paper here. So here, typically when we apply the loss in machine learning or deep learning, we apply the loss for all of the inputs. But here, as is specifically stated, they apply the loss only for the masked input. So that's very important. That's one of the important things that is mentioned in the paper, which is a key piece. Okay, so this is really the training process. So we have to discover these hidden units or the targets, and then in the second step, we train the model to predict the hidden units or the targets for the masked positions of the input. Now, one important thing that I would want to mention is that, remember in the beginning I said that in the first iteration, the authors used MFCC features. Now, I want to emphasize again, those MFCC features are only used in the first iterations. So what's happening is, during the training process, let's say now we are in the second iteration. So in the second iteration, these inputs that are going into the first step, which is to discover the hidden unit, these inputs are not the original MFCC features. This input is actually taken from the intermediate layer of the transformer network. So from here. And then based on that set of input, we do the clustering again and we come up with the new targets. And then in the second step, we again mask some of the input, and then we ask the model to predict what is the embedding or what is the missing part of the input, and we do the comparison with these targets, and then we calculate the loss, and again we repeat this process. So the key thing is that for the prediction step, for the first step, which is to discover the hidden unit, it's only during the first iteration it takes the MFCC features. For rest of the iterations of the training, what it takes is the intermediate output from one of the transformer encoder layers. That's very important. So that's really what the training process is. Now, I want to go back to the original paper and try to compare this diagram with the original diagram in the paper. Okay, so let's look at this. So this is what we were looking at right now, and this is the diagram from the original paper. They're actually similar, except that here in the original paper they compressed everything into one diagram, which makes it harder to understand. However, now that we understand this, if we come back to this, I think we will understand what they're trying to do here. So here, the input to the model is the raw waveform. It's a continuous input. And the dotted line here is just showing us the step 1 of the process. So first, from this continuous input, we apply clustering technique to find what the hidden units are, or in other words, what the targets are. And this is Z1, Z2, Z3. What they're not showing explicitly is that in the first iteration they use MFCC features, in the rest of the iterations they use the output of the transform. So it's not explicit, but that's why I wanted to show you this diagram first. So we have created these targets, and then in the second step of the process is predicting the targets for the masked input. So here again, the input is the raw waveform. First, we find the latent features, which converts this raw waveform to discrete units, and then we intentionally mask some of the inputs, and then the goal is that we want the model, this transformer model, to learn to be able to predict the targets for the masked regions. So that's really the HuBERT. So this whole thing is called the HuBERT model, including the CNN encoder and this framework, and then this transformer or BERT encoder. So that's really what the HuBERT model is. Now, it may not be very clear what I explained because this honestly is a little bit complicated. So I would encourage you to read this paper a few times, and also I would highly encourage you to read this blog, because it clarifies a lot of things. And then if you have further questions on this, I encourage you to ask those in the comments below. I think I'll stop here, and I hope this helped. Again, if you have more questions, please feel free to ask those in the comments below, and I would be happy to answer the questions. With that, thank you, and I will see you in my next video. Thanks.